Hey guys, I hope everyone can hear me okay. If not, let me know. Um, it's currently very early in Chicago, where I am. So if I sound groggy or sleepy, it's because I am. Um, yeah, so if anyone has any audio issues on my end, please let me know now. Okay, can someone confirm that they can hear me? Okay, awesome. Um, yeah, so um, I think some of you probably know me or have taken classes with me before. My name is Ajit Chandra. I'm a current PhD resident here in Chicago. I'm I'm working with Rush University currently, and I'm actually going to be defending my dissertation in about 3 weeks. So wish me luck on that. So I know a thing or two about research and its applications and the method that you guys should be using to apply it. And I hope to at least introduce some of the concepts to you. Um, Again, so I'm currently in like a cafe because I needed coffee badly. So again, if you guys hear some other ambient sounds, it's because of that. Um, Yeah, so what we're going to be doing today is about, I would say, 30 minutes to 45 minutes of an introduction and an overview to what research is. And before, when I would do this class, and I've done this class many, many times, I would go through multiple methods of research. I would go through very complicated things like hermeneutics and very like philosophical concepts. And what I kind of came to understand is that that wasn't really helpful for you guys. Um, I think I think mainly what a lot of you are going to be doing is going to be applying the scientific method in specifically. So I wanted to focus in on exactly what makes this form of research special and how you guys can apply this form of research. Because probably, most likely, 99% of students that I've talked to have um, are applying this. Um, so let me guide you through some of the introduction uh, into this method. I'm sure that a lot of you have gone through similar stuff before, so it might be review. But if you have any questions or comments, you can either put it in the chat or just feel free to interrupt me as well. Okay. So basically, the point of this presentation is to detail the process of the scientific method. I'm also going to highlight some applications of it I find that it's really helpful to see how scientists and researchers came to their conclusions and kind of the logical processes that they took. It kind of helps demystify the entire process to see like, okay, even very famous Nobel Prize winning people uh, had a system and followed a method. So I'm going to be doing that as well. I'm actually going to be exploring some of the limitations of research and um, what is outside the boundaries of what you can and cannot do with this realm. And I'm also going to give you guys a small assignment. So hopefully next time we can go through the assignment together and see if you fully encapsulated this this method. So the first thing that we can do is of course, right, it's science. We're going to be defining things. And one definition of research that you can give is it's a systematic investigation into a problem or a situation. And the key word here is systematic. Um, the entire idea of separating research from just searching on Google or just doing your own investigation into informal investigation into a topic is the idea that you are being systematic about it. Are you recording your search terms? Are you making sure that you have a history of your sources? Are you making sure that the validity of your sources are good? Are you exacting exactly what the results are from what your hypothesis was? So it's what separates research from a lot of everyday activities that you do is only paperwork, right? It's only the stuff that you have to do to make sure that everybody understands what you're trying to get at. I find that a lot of students get very anxious about how to do this, and they don't know where to begin, and especially when they're working on their own projects. And I always try and tell them that, like, it's the normal things that you guys would do if you're trying to find the answer to a question. You guys would use the internet, you guys would use books, various things. And it's a similar process. It's just you're being very systematic about it. So I want you guys to keep that in mind when you're eventually doing your own research project. And here's another definition. This one includes more the idea of gathering of data, information, and facts. So this kind of introduces the concept that research ideally is supposed to be primary research, right? It's things that you're answering a question that perhaps has never been answered before. And this is one of, I think, the very unique things about this field is, unlike in other fields where it's very application based, and that has its benefits too. You're always treading new ground here, or you're trying to, right? You're always doing something that ideally no one else has done before, and that can be a very special feeling to know that you're kind of on the cutting edge. Okay. So, as I said, the scientific method is kind of one way that you can apply research, right? It's an empirical method, and if you guys aren't familiar with empiricism as a topic, it's just a word that just means that the way you get knowledge is to experiment and to test the world and see what data you get from the world, right? This is as opposed to perhaps a philosophy like rationalism, which is kind of like internally, like mentally, you are connecting logical systems together. Like, think of math versus physics. They're both kind of similar. You're using a lot of equations and formulas, but in physics, you are testing the world. You are dropping an object off the Leaning Tower of Pisa to see if a wooden cannonball and an iron one fall at the same rate, and they do. So you're actively testing the world, and that's the key part of science here. But the actual kind of formula, I guess, if one could say, is the first part is to, of course, formulate a question and a possible answer. The hypothesis. And if you guys watched the video that I sent of Richard Feynman, I hope everybody watched it. I think Feynman is a Nobel Prize winning physicist, and not only that, he has an excellent mind for education and kind of telling people in a very simple way very complicated topics. And I think this is one that he addresses really, really well, where he talks about how science has a lot of guesswork. And it's true. a lot of what you're going to be doing when you're eventually doing your own project is just thinking of a good guess for the question that you have. And this doesn't have to be in physics. It doesn't have to be in biology or any hard science. It can be in economics. It can be in finance. I've had students before who were curious, like their question was, is some form of renewable energy source possible in the villages of Mumbai or the villages near Mumbai? And this is a very kind of abstract, you know, economic, finance, environmental, energy-based question. But the scientific method is about the fact that you can apply any genre, any research topic, and get some kind of rigorous empirical answer. So it all starts from, as I said, a question. And we're going to be talking more about what makes a good question and what makes a bad question. But kind of to summarize it, a question should not be vague, right? It shouldn't be so broad that every possible field can fit inside it, or you know, or be so broad that it becomes impossible to test or test well. Um, and so this is what a good question entails. So what entails a good guess? Well, a good guess is something that you can extrapolate the consequences of, right? This is the key portion of even this lecture. I would say if you guys can understand the jump from hypothesis to the consequences of the hypothesis, then that's enough for this class. Because you know, I find that some students struggle with this concept of extrapolating the consequences. And sometimes they struggle with it because they came up with the hypothesis that is overly broad or incredibly narrow, and they can't think of the consequences. So we're going to be going through some applications of this, and I hope you guys can understand this. But for now, yeah, so you come up with a guess, you come up with the extrapolations of what that guess might entail, and then you test the prediction in an experiment. And then the final portion of this, because of course you're being systematic, you're not just arbitrarily doing this for, you know, your own benefit. You are recording it and reporting it. And so you're going to discuss results of the experiment, and finally, whether your hypothesis was true or false. And either way, it's fine, right? You're not graded on how good you are at guessing. You're graded on how good you are at creatively talking about and discussing why you were right or wrong. So this is a helpful flow chart that you guys might want to refer back to when you do your assignments or down the line. So I find that a lot of times asking questions and doing background research is very, very easy for students. If you guys have written essays, if you guys have written, you know, any kind of scientific, you know, a lab report or something, these first two steps are relatively simple. It's, as I said, constructing a hypothesis and testing with an experiment and figuring out, okay, how do I test it? What are the consequences? These are the harder parts of this. And so, but, you know, as I said, you're testing with an experiment. You're figuring out if that experiment is viable, if it's working, and then you're analyzing that data and you're drawing the conclusions, and then you're communicating them. And what I like about this flowchart also is that it refers to the idea of research as a cyclical project, that once you get this information, whether you were right or wrong, it becomes fuel for new research and new questions, and in this unending loop of science and research. And I find this is very true. In my field, a lot of my best ideas and questions came from previous projects, whether they were technically failures or successes. Okay, so let's talk a little bit more about the actual guess, right? About the hypothesis. Um, it's important to remember that this hypothesis, it's a theoretical concept, right? It's not some concrete law, like you have to do the hypothesis, and you have to do it in this specific way. The hypothesis is there to help you. It's there to help you think about um, your 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 project. It's there. It's kind of a tool that you have um, in your toolbox. And there are sometimes where a hypothesis is not totally necessary. There are sometimes where alternate hypotheses are possible. Um, but yeah, I want to make clear this concept that you are using the hypothesis. The hypothesis is not using you. You are be creative about how you approach the method, and um, but the hypothesis is a really helpful tool to help you think. Okay, I have this question, and how do I even start to approach it? And so having an initial guess can give you guys kind of an idea like, okay, at least I can start by proving this right or wrong. And that's the entire point of it. Okay, so if you guys have any questions about kind of these first few topics, let me know and we can address that. But otherwise, we're going to go over some of the applications of this. And then I'm going to take some more questions and we're going to be done. So I hope you guys know who Crick and Watson are. Um, they were the two central people, well, two of three, I suppose, but they were two of the central figures that came up with the structure of DNA. And in 1962, they got the Nobel Prize for it. So yeah, so they were both theoretical molecular biologists, and it might be really hard from the outside to even see to even see how did you even start, like how did they even begin this process, right? Um, but if we break it down from a with this method that I was talking about, I think it becomes a little more clear. So if the question is, what is the structure of DNA? Then they guessed, right? They had a guess. And you might say, okay, where did they come up with this guess? How did they just happen to get upon the exact answer? And this is where scientists can be better or worse at guessing. Um, so they come up with this exact guess because they had a theoretical background, they had various mathematical tools. People already were suspecting that it might have had a helical structure. Um, so there's a lot of background context here. But the key point here that I want you guys to understand is that they didn't know. They didn't know if it had a helical structure. But they knew that if DNA did have a helical structure, they knew what a testable consequence of that is. And the testable consequence of that is that the diffraction pattern, which if you guys have ever taken physics or anything like that, um, you know that implies kind of it's similar to the shadow when it's hit with some form of radiation. And specifically when it's hit with X-rays, it's going to have a specific X shape, right? And they came up with this prediction because of various knowledge that they had with how diffraction patterns work and how certain structures have certain patterns. Um, so yeah, so they were able to come up with a guess, and then they were able to come up with a consequence of that guess. And this is the key step that separates, groundbreaking science, Nobel Prize winning science from just talking with your friends about what could or could not be. This step from guess to prediction. And I think this is probably, even for me, this is the hardest part in terms of research and science. So again, if you guys have questions about what a prediction is, let me know. But I think that when you guys eventually do your own assignments, this is going to be the part that you struggle with the most. And I hope you'll come back to these slides, which I'm going to send to all of you. And hopefully, you're going to be inspired by these. But yeah, so the experiment that they did was they hit crystallized DNA with this particular form of radiation, and an actual photo was taken of the diffraction pattern, and the photo can be seen. Right? When I look at this photo, it demystifies so much of what great science is, what great research is. It can be really easy, as I said, to kind of be so in awe of this kind of the greatness of this kind of discovery that you don't realize that at the end of the day, these scientists took a photo and looked at it and said, okay, yeah, you were right. And it can be something that we all can do if we think of the right question, the right guess, and make the right prediction. But yeah, so of course, as you guys can see, the pattern was seen to be in an X shape, and their conclusion was rightly that DNA has a helical structure. And you guys can actually, the paper that they publish is available online. It's amazing. It's like 3-4 pages long. It's not very long. You'll find it common that some of the greatest scientific discoveries were published in papers that are like 2-3 pages long. I think Einstein's special relativity paper was like 1 page long or 2 pages long, in very simple language. So, this is just a reminder that complicated and overly long does not mean right. And of course, I don't want anybody to forget about Rosalind Franklin, who was a key third member of this team. She was actually the person who actually did the crystallization of the DNA, which is a key component of this entire experiment. Unfortunately, throughout history, she's kind of been ignored. So it's good that people are still talking about her. I just think that she didn't get the Nobel Prize for various reasons. So, okay, well, let's go back a little bit further in time, and let's go back 1,000 years in time, in fact. So Ibn al-Haytham was an Arab scientist, philosopher, mathematician. I always get jealous of when I read about philosophers and scientists and researchers from a long time ago. It seems like they did everything. Like they did physics, they did biology, they did every possible topic under the sun. And I think it really lends them this I don't know, this like mystic air, but that might just be me. But so this man, he lived specifically under the Fatimid dynasty in Cairo, and he wrote very influential. He wrote a lot of influential books, but probably his most famous one was on optics and light. And so one of the questions that he tried to answer was exactly how is it that we use our eyes? And this question might seem incredibly trivial now, but you have to remember that we stand on the shoulders of giants, right? We stand on the bedrock of knowledge that's been built up by people kind of applying this kind of method and this kind of rationality over hundreds and thousands of years. And so even a basic question like this, like how do we use our eyes? It wasn't totally, it wasn't totally known. Are our eyes like flashlights? Like, are we emitting light from our eyes and then it reflects back? Or is light just purely from other sources? Is light curving around corners, or is it traveling in straight lines? And so his hypothesis was that light enters our eyes from other sources, and also that it travels in straight lines. And you guys might think, okay, like, what is a prediction of this? How can we possibly test something like this? And again, so this is, again, and I'm going to keep harping on this point, to me, the real creativity of science and research comes in this step from guess to prediction. And so his prediction was that if light enters our eyes and it's not produced by our eyes, then when only one light source is nearby and then subsequently covered, then our vision should darken. So what he actually did was he stood in a very dark room in like some sort of tent, I think, and two small holes were cut that allowed the light of two nearby lanterns to go through. And so you could see the spot that they made on the other side of the tent. And then when these lanterns were then subsequently covered, the spots of light they created were also darkening. And so he came to the conclusion that, sorry for the noise, by the way, but yeah, he came to the conclusion that light is not created by our eyes, but it enters our eyes. Yeah, so another application of this. I hope you all know who Fleming is. He was a bacteriologist, and when he was serving in the First World War, he saw that most of the deaths that he was trying to solve didn't come as a result of blood loss or something like that. It actually came as a result of infection, of antibacterial, or the lack of antibacterial help. And so, of course, what he did was, and what he's known in history for, is discovering penicillin, kicking off the modern era of antibiotics. I'm actually on a course of antibiotics right now, so thank you, Fleming. Okay, so I think some of you might be familiar with this famous story, but it's one that's kind of infamous in science and medicine. That story goes that Fleming, he was an eccentric man, and a lot of the experiments he did, he just kind of laid out. So he would have molds of various things that he was testing, of various fungi and various just plants and fauna, and one of these and on one of these kind of plates, he saw that this mold was growing, and when he came back and actually found this, okay, one of my plates has been contaminated, he was amazed to see that around this mold there was a ring where there was absolutely no bacteria. And so what his guess was that that this particular species of mold, it produces substances that are deadly to bacteria. And again, to me, this highlights another key point of what a researcher has to be, which is curious and observant. I'm sure that many of us, if we came back home and saw that one of our carefully, one of these things that we had carefully worked on is damaged or grown with mold, we'd just be angry and throw it out. But he had the insight to, and the curiosity to wonder more. And so this is what I kind of the focus of what, or what at least what inspires me about this particular story. But yeah, so his guess was that it's the mold that's producing substances that's deadly to bacteria. And thus, of course, the prediction is that if this mold is reintroduced to other bacteria-rich environments, the bacteria should die. And so eventually he isolated and purified samples of this penicillium, or notatum, as you call it, and he introduced it to other bacteria plates, and the results were immediate. A wide variety of bacteria were killed using these isolated mold samples. And the other point that I want to make clear here is, remember when I said that research is cyclical, that the questions don't just end because you come to the conclusion. They're a fuel source for new questions. So what's the next step here, right? We know that this mold uh, can help kill bacteria. Okay, now how do we apply this? How do we get this to the people who need it the most and in vast quantities? So the next question was how to purify and mass produce stable penicillin, which is the active ingredient in this mold. And it's actually not Fleming who did this. Fleming published this at some point right after the war, and actually no one really cared. You know, it was just kind of an obscure thing in an obscure journal. And it was when a pair of British scientists tried to actually mass produce it that it became as widely known as it is. Of course, we still credit Fleming for the actual discovery of this, but I want this to highlight the fact that support roles are also important, vital in research. Taking somebody else's work and saying, what's the next step here? How can we apply this? How can we give this to more people? How can we help a very specific group of people? So research builds off of each other. No one stands alone. We're always working off of the work of other people, and that's to, I think, the credit of us all. So here's a very silly application of this. So the question might be, why does my hotel room smell? And we're going to kind of go through the actual application of this method in this very silly way. But so if the question is, why does my hotel room smell? You guys can either type in chat or say like, what's a possible guess, right? Like you have no idea, but what's a guess? Okay, I see rancid food. Yep, that's a great guess. Okay, so if it is in fact some kind of food, and in fact I think I said as something. Lahar jumped straight to dead rodents. I don't know why I'm keeping dead mice in my closet, but that's also a possible, that's also an option. But if we stick to rancid food, what do you guys think is a prediction? Okay, so I'm guessing that leftover food in my fridge is causing the smell. And actually, Adam, I want to use your point to say you want to be a little more specific about your guess, right? So rancid food, okay, but like, what is its location? Where is it in the world? Um, this this kind of specificity helps you jump from the guess to the prediction. So in my guess, I was a little more narrow, and yeah, awesome, yeah. So you left it in the microwave specifically. That might be a much more testable guess, right? So if we use your example or mine, what do you guys think a prediction is? Like, how could you test this? Right. One way to be would just be to open my microwave and smell, um, or open the fridge and smell. But um, think about ways in which you can eliminate as many. Um, and of course, again, I want to make it clear, like this is not a right or wrong answer, and also it's a very silly question. So you guys don't have to think too hard about it, but the point of this is to help you guys come up with your own predictions. And one thing that I find helpful in my work is to come up with a prediction that can kind of, for sure, like you can definitely rule out whether it's wrong, right? You're not going to be sure it's right, but at the very least, you're going to be sure that if this prediction is wrong, then you kind of know where you're starting from. You know at least that your guess is wrong. So one of the problems with kind of an open-ended thing like just opening up a fridge is, what if I smell the fridge and the fridge smells, but so does everything else, and I'm still not entirely sure. Again, so this is a silly application of it, and I'm not even sure if that makes logical sense. But the prediction that I made was that removing this particular food item from my fridge and throwing it away, and removing it from my room altogether, should eliminate the odor in my room. Yeah, so that's the other thing about the prediction, is that the prediction is not just how you're doing it. The prediction is also exactly what the guess entails. So if we use your example, Adam, about you using the sense of smell specifically, the prediction would be kind of worded like, the smell should be strongest. Actually, yeah. So your second point is exactly right. The smell should be coming from where it's located the most. But using my guess and my prediction, the food was removed from the fridge, and the subsequent smell was tested. And if this experiment is carried through, and we see that my room no longer smelled after the removal of this food, then the conclusion is that my hypothesis was right and my guess was right. And so this is one possible kind of scenario to help you guys go through. So let's run through some more examples. So is it raining outside right now? And let's say you guess yes. What do you guys think? What do you guys think is a prediction of that? How could you test that guess? And specifically, you have to. So Adam said, look outside, and of course that's the direct thing that you would do, but that's not a prediction, right? Looking outside isn't a prediction. If you said, so in this specific example, you would say, I should see rain when I look outside. And I know that this might seem like a trivial point. Yep, that's another. You guys are really getting the point here. Exactly. Yeah. If there's rain falling, it is raining. Do you hear the sound of rain? If yes, then it's, yeah, etc., etc. These are all great points. But the jump from the guess to the prediction will always be the most difficult point, I think. And so I really wanted to be clear, and that the prediction has to be something that when you make it, you immediately know, okay, I know how to test this. It's another tool, like the hypothesis, that should help you guess this point. So let's run through one more time with another question. Is my friend angry with me? And you guess yes. How could you, what's the prediction? What's the consequence of your friend being angry with you? How could you test that? Right, you ask her, and then what would be her response, right? Like, remember that it's a prediction. Right, exactly. That's a great one, Adam. Yes. So in Adam's response, there's a specific thing that you can test, and there's a specific response that he's waiting for, right? So if X doesn't happen, then Y is this. And so that's a great one. Yeah, if she doesn't like the real pictures, or she might be like me and just not sure how to use Instagram. Um, so, but yes, great job, guys. Okay, we have a little bit more time, so let's quickly run through some of the pitfalls of research. We kind of talked about how great it is and how, Fleming saved millions of lives, Crick and Watson, million, just through knowing all this stuff, like, how many countless lives has research saved. But it's also affected lives negatively. In 1998, a doctor named Andrew Wakefield, I think he's no longer a doctor, but he published a study in the Lancet that established a link between autism and the MMR vaccine, the measles, mumps, and rubella. Um, and it was later found that he had broken numerous codes of ethics. He had made up a bunch of his data. He had lied, just flat out lied about a lot of stuff. And his paper was eventually, I think, removed from the actual journal, but it was too late. And to this day, people still talk about the link between autism and vaccines, and people don't vaccinate their kids. I think it's actually more rare in India. Um, exactly, Adam. It's actually like in America, it's crazy. A lot of very intelligent, very wealthy people don't vaccinate their kids because they're afraid of autism, and it all kind of comes back to this fraudulent um, link that this man found. Um, so I kind of wanted to highlight the downside as well. And another interesting example that we don't quite have time for today is yes. So like um, another consequence was, I'm sure you guys are familiar with uh, with Oppenheimer. He was the head of the Manhattan Project, and he was kind of the scientist leading the charge towards the development of atomic weapons. And so this quote is him remembering how he felt when he first saw the first test of the first atomic bomb. Um, so it's quite a somber moment for me, a sober moment, because all the work we do have consequences in the real world, and for good or for ill, it's going to affect the world in some way. And so, we should at least have some thoughts on how our research might be used. Okay, I'm actually going to leave this stuff to the next class. Um, and uh, yeah, I'm going to leave it to the next class. We kind of began our next class with talking about these experiments. I think these experiments are a really cool way to talk about, the question, the hypothesis, the prediction. So we can kind of review the method you using this experiment. Um, Maybe some of you have heard of it already, but we can review it next week. But I do actually have an assignment for you. So the assignment is, I want you guys to kind of, how we went through that process? Like I asked you guys a question, you came up with, and I gave you guys a guess, and then you came up with a prediction, and we tested it together in this kind of made up world. Well, I want you guys to lay out a similar method, but for an actual scientific discovery that you're interested in. So other than the examples from like our class, so if you're interested in say in economics, then find a really cool economic thing that was discovered and introduce it to me in this kind of way. What was the initial question? What was the initial guess? Well, what was the prediction? How did they test it? And it can be one line each. I want it to be very, very brief. If this isn't an essay, it's point form notes. So, I would say even like 10 to 15 lines. That's all I need. But I want to be sure that you guys kind of understand and can do by yourself this process of jumping from question to guess to prediction
the results. So again, find a discovery that you're particularly passionate about or interested in, and lay out the method that was used, and send that to me personally. I'm going to type my email in the chat, and you guys can make a note of it. Um, so please send it to me before Saturday, before next Saturday. And so I can review some of it and give you guys individual notes when we get back to class for next Sunday. So if you guys have any final questions, let me know. But my kind of final concluding thoughts here are, I hope that this introduction and this class kind of at least gave you guys an idea of what the method is, right? What are people thinking about when they're starting out on answering a question? And next week we're going to go into a lot more details about, okay, how exactly will you do this? How exactly will you come up with a question even? You know, how are questions made? So we're going to be breaking down point by point by point, like how to do each of these steps. But for now, I hope I gave you guys an overview that you guys can come back to again and again. Mahar asked, will the end product be a research paper? I still have to talk to Professor Sham about this, exactly what the end product, but that, for me, that is the goal for you guys to end, if not a research paper, at least a review or an article of some kind, something that you guys made that you're going to be proud of and present and publish in a journal if you'd like. So that's really the goal. But I'm going to talk to some of the organizers and see if we have time for that and how many classes that we have. I believe we've scheduled 3 or 4 classes in the next month. And so how far we can get with that, you know, I'll get back to you guys on that. But for now, if no one else has any other questions, thank you so much for attending. And if that's it, I'm probably going to go back to sleep soon. So 6 a.m. just hit, and I slept at about 12 p.m. So, all right, thank you. I hope everybody has a great day, and see you guys next week.